let's start the session. Welcome participants. We are continue having very interesting sessions throughout the conference, and today afternoon we have a very renowned speaker, Professor Eudes Borges de Araujo. He is going to talk on the topic defect control and its implications in Bismuth Ferrite thin films. A few more words about Professor Araujo. He's a full professor at Department of Physics and Chemistry, São Paulo State University, Brazil. And he's graduated from Federal University of Ceará, Brazil. And he obtained a PhD from Federal University, São Carlos, Brazil. Right. His main research interests are ferroelectric and multiferroic thin films and piezoelectric materials. Right. Thank you, Professor Araujo, for accepting our invitation. Kindly, it's now your time. Please talk the presentation.
Okay. Good afternoon, everyone. First of all, thank you, Mr. Chairman, for the introduction. Also, I would like to thank the organizers for the invitation. It is a pleasure for me to attend this conference again. In my talk today, I would like to review some of points regarding the defect control and its implications in bismuth ferrite thin films. The outline of my talks includes a brief introduction, some discussions regarding difficulties in obtaining bismuth ferrite thin films and its consequence in terms of defects and physical properties. In the second part of my talk, I will present some of our recent studies on BFO thin films prepared with the different stoichiometries to investigate the contribution of complex defects on their physical properties. Of course, comparing these properties with the recent results in the literature. Finally, a summary closes the talk. In the first part of my talk, I would like to review some of the physical properties of BiFi-O3 thin films, as well the importance of defects on their properties. Introduced in 1950s, the bismuth ferrite is a prototype multiferroic material at room temperature with a ferroelectric and antiferromagnetic phases. In the blue arrow in this figure, we can see the polar axis in the BFO crystal structure, while the red arrows indicate the magnetic moments. So the BFO is well known for a large ferroelectric polarization observed in thin films at room temperature, as we can see in this ferroelectric hysteresis of an epitaxial BFO thin film. The ferroelectric domain structure in BFO is exciting from the scientific and technological points of view. In this figure, the schematic diagram of the 180, 109, and 71 domains is shown in the BFO crystal structure. These domains were indicated in this PFM image. For this and other reasons, the BFO has been studied for potential application in multiferroic devices in past years. However, unfortunately, a large leakage current is often observed in BFO thin films at room temperature. The use of single crystal substrates, the construction of modular structures, the use of cation substitutions, etc., has been often used as strategies to control the leakage current in the BFO film. In addition to the large ferroelectric polarization, a large open circuit voltage and the photovoltaic response of BFO films has been an important motivation to study this system. Recent studies have been shown that its photovoltaic response can be improved by controlling the defects, as observed in this figure for BFO thin films with different bismuth stoichiometry. Despite these advances, the physical mechanisms behind the photovoltaic effect in BFO are still unclear. So it is essential to review the origin of these defects in BFO system to understand the role of these defects on their physical properties to promote the desired technological advances. In principle, the BFO3 phase is thermodynamically stable in a wide range of temperatures, as we can see in this phase diagram of the bismuth oxide, iron oxide system. However, this stability is a controversy in the literature that remains an open subject. Despite this controversy, more and more evidence has indicated that Bismuth Ferrite is not thermodynamically stable. It is one of the most critical difficulties in obtaining BFO3 phase. As a consequence, different defects can be introduced in BFO system during the synthesis of ceramics and thin films. Due to this instability, the final product often contains some impurities, which leads to an increase in its electrical conductivity. Other difficulties, such as the inappropriate control of precursors, the high stability of the intermediate phases, and the loss of oxygen can also influence the BFO electrical conductivity and other physical properties. Regarding the inappropriate control of precursors, it is important to note that the bismuth and iron nitrates often used in chemical solution deposition are highly hygroscopic. Then the inappropriate control of these precursors is a critical problem of stoichiometry deviations in the final composition that must be considered during the film synthesis. All these difficulties lead to low reproducibility and inconsistent results in the literature. Okay, we are talking about defects in the BFO system, but what are these defects? In their seminal work, Paulo and co-authors summarized the intrinsic defects in BFO in this work. They observed that bismuth, iron, and oxygen vacancies are present in the BFO system, but in oxidizing conditions. But the bismuth and the iron vacancies are dominant defects under these conditions. On the other hand, in reducing conditions, the oxygen and bismuth vacancies dominates. It is interesting to note that the bismuth and iron vacancies produce a magnetic moment for P-type BFO and known for insulating BFO. In contrast, oxygen vacancies does not introduce any moment for both p-type or insulating VFO. More recently, Genestein et al. Confirmed the p-type and n-type conditions in VFO. In addition, they assumed that beyond electrons and holes, oxygen, iron, and bismuth vacancies with the different oxidation states are possible in VFO. And the presence of cationic and oxygen vacancies can lead to possible imprint effect in VFO system. In this complex scenario, we prepared a set of Bismuth Ferrite thin films with the different stoichiometries to investigate the effects of different defects on their physical properties, focusing on the dielectric and electrical properties. So this table summarizes the main conditions of the studied BFO thin films prepared by chemical solution deposition. The EDS technique was used in this system to quantify the film's stoichiometry, while the X-ray diffraction was used to study their structures. Based on XPS analysis, we observed, summarized in this figure, we observed the presence of both iron 3+ and iron 2+ for all studied films, as indicated in this figure A. In figure C, we observed oxygen vacancies with different oxidation states for all films. The oxygen vacancies concentrations is higher in BFO3 film and is smaller in bismuth deficient BFO2 film. This data will be important for the next discussions. Regarding the dielectric properties, no pronounced dispersions were observed in real permittivity, as we can see in this figure A. And no dielectrical relaxations were observed in our films, as sometimes observed in the literature, as summarized in this figure for a BFO film prepared by a chemical route. In this case, the dielectric relaxation could be suppressed by introducing 5% of zirconium. In our case, at the room temperature, this dielectric relaxation were not observed in principle. Another important result in this figure is that the imaginary permittivity reveals samples with different conductivities profiles. The temperature dependencies of dielectric permittivity of our studied BFO films were very similar, as we can see in this figure. However, for BFO films with multiply layers depositions, pronounced peaks with frequency and temperature dispersions were observed in real permittivity, as shown in these both figures for BFO films prepared under two different conditions. The first one was crystallized in air, and the second one in oxygen atmosphere, For these films, we observed the observed relaxor-like behavior is an artifact, probably due to interfacial effects. As you know, the BFO system is not a relaxor material. Okay. Moving to the next, we can see that the crystallization kinetic effects such as rapid thermal reading and slow thermal reading, change the shape of that curves, but the peaks remain as observed in these figures. It is an important result because it suggests that we need to control the defects during the synthesis. If a BFO film will have a specific defect, such as oxygen vacancies or bismuth vacancies, it is or interfacial defects. We can see from this result that is impossible, practically impossible to remove these defects after the synthesis. For impedance and electrical modulus spectroscopy analysis, we used the traditional bricklayer model to discriminate between the grain and grain boundary effects in the impedance and electric modulus. In this figure, we can see that the typical dielectric relaxations in our films. In addition, we also can see that no electrode effects are present in our films. The temperature and DC bias electric field effects were also studied, as summarized in this figure, showing similar effects on the dielectric relaxations for temperature and electric field, shown in this figure for the BFO3 film. In addition to DC conductivity, several parameters were obtained for all samples from fitting the Nyquist plots for impedance and electric modulus, as shown in these both figures. You can see in the inside plots a perfect agreement between experimental data and the theoretical model proposed to fit this data. From asymmetries on the Nyquist plots of electric modulus in this figure, we could infer about the defects in BFO films, similar to the fatigue effect observed in this film in this BFO film prepared also by chemical route. Additional analysis on AC conductivity for all studied BFO films was conducted using the junction power law model. The obtained DC conductivities from these from fitting these curves were essentially the same as that obtained for grain boundaries from impedance and electric modulus spectroscopy. From all these analyses, the temperature dependencies of relaxation time and DC conductivities of grain and grain boundaries were summarized in this figure. From linear fit in all these curves, we summarized the activation energies in this table for the grain and grain boundary. Based on these values, the activation energies were associated with the first and the second ionization of oxygen vacancies. Well, it was the summary of the dielectric measurements. We observed no drastic differences between our results and those reported in the literature. Let's move now to the electrical properties, the final part of my talk. But focusing on the leakage current and photovoltaic response of the studied BFO films. So the leakage current does not depend on the deposition method. It is observed in BFO thin films prepared from chemical or physical routes. However, the leakage current can be changed by introducing some kind of dopant atom, as observed in this left figure, or tuning some specific parameter during the synthesis, as shown in this figure on the right. It is important to note that in the right case, the leakage current has been suppressed by 2 orders of magnitude, increasing the growth rate. On the other hand, in the BFO film prepared by chemical route, we observed that leakage current was suppressed by at least 5 orders of magnitude, introducing dopants like as lanthanum and niobium. On the other hand, changes in the bismuth stoichiometry also lead to BFO films with different leakage currents, as observed in this figure from a recent work of Young et al. Published just 2 years ago. Okay, in this case, the leakage properties were attributed to the change in the oxygen vacancies. Young et al. Concluded that bismuth vacancies increases the oxygen vacancy concentration, while bismuth in excess decreases the oxygen vacancy concentration in their BFO films. In other words, in their opinion, the oxygen vacancy concentrations has a high impact on the leakage current of BFO films. Different mechanisms have been reported in the literature for the leakage current. The most common, the most used are the ohmic, the space-charged limited conduction, Schottky, Polyfrankel, and Fowler-Nordheim mechanisms. Young et al. Concluded in their study that ohmic conductions occurs at low electric fields, while the Schottky mechanism dominates in the high electric field region, as summarized in this figure. Okay. Finally, they concluded that the photovoltaic response in their BFO films was intrinsically related to the oxygen vacancies concentration. In other words, lower oxygen vacancies concentrations leads the blue curve in this leakage current leads to a high photovoltaic response, as observed in this figure, while the low photoconductivity response was observed in BFO film with high oxygen concentrations, vacancies concentrations. We performed a similar study in our BFO films. This figure summarizes the leakage current of our studied BFO thin films. As shown before, from ADS and XPS quantifications, the bismuth iron ratio is higher for BFO1 film, lower for bismuth deficient BFO2, and intermediate for BFO3 and 4. For these two last sample, 3 and 4, the bismuth iron ratios were almost the same within the instrumental error. On the other hand, from XPS analysis, SPS analysis as summarized in this line, the oxygen vacancies concentration was higher for BFO3 and smaller from the BFO2 film, and intermediate values for BFO1 and BFO4. Remember the composition of these films shown for you in the table, in the previous slide. Okay, excluding the BFO film, we observed that oxygen vacancies concentration is directly proportional to the bismuth amount in our films. Okay, this result does not agree with Young et al. Results shown previously. They observed or concluded exactly the opposite. Their films with bismuth in excess results in lower oxygen vacancies concentrations, while bismuth deficient film produces higher oxygen vacancies concentrations. We excluded the BFO film, but what can we say about the BFO1 film? For this specific sample, we reported in recent work that a strain polarization coupling mechanism enhances the conductivity at the grain boundaries. So additional studies are in progress to better understand the relationship between leakage current in this film and this specific mechanism. Regarding the leakage mechanism, we excluded the SC-LC mechanism for all BFO films in this figure B, but ohmic conduction dominates at low electric fields except for BFO1. We verified the possible Schottky mechanism in this figure C. Despite the excellent linear fit as shown in these figures, the obtained dielectric permittivities at optical frequencies were unrealistic as observed in this figure. So the Schottky mechanisms were discarded for all our studied BFO films. On the other hand, we checked for the Pulley-Frankel, for the possible Pulley-Frankel mechanism in this figure D. In this case, the linear fits in this figure D leads to consistent values for the optical dielectric permittivity. Finally, we also check for the possible Fowler-Nordheim mechanism as summarized in this figure. This mechanism was discarded for both BFO3 and 4 films as indicated in this figure. However, for the BFO film with bismuth in excess, the BFO sample, the BFO1 sample, and for the bismuth deficient, the BFO2 sample, this mechanism is possible at high electric fields. Finally, the photovoltaic properties of these films were also studied. Comparing the photovoltaic properties with the leakage current, we concluded that the photocurrent density follows the bismuth iron ratio in these films. In other words, the photocurrent density follows the oxygen vacancies concentrations in the studied BFO films, except for BFO1. Since the photocurrent of BFO1 is not the lowest, as we can see in this figure, it suggests that the leakage current and the photocurrent does not only depend on the oxygen vacancy concentrations. Probably competition between different defects is responsible for these physical properties in BiFi O3 thin films. So our suggestion is that these properties must be investigated in details for the next in the next studies. So, in summary, we observed that the control of different parameters is essential to the reproducibility of BiFi O3 thin films. On the other hand, the common defects in BFO thin films, such as bismuth vacancies, iron vacancies, and oxygen vacancies, have a profound impact on its physical properties. And finally, the described scenario indicates that additional investigations are still needed to change the paradigm of BiFi-O3 as a potential material to realistic material for technological applications. Okay, to finish, I would like to thank my students directly involved in this research, and also our colleagues in Russia and Portugal and Brazil. And especially, thank you very much for your attention. Thank you.
Thank you. Thank you very much, Professor Araujo, for the very interesting talk, and it's quite informative. If there are any queries, Professor Araujo would like to clarify it. Is there any question from the participants? You can raise your hands or you can directly unmute and talk. Is there any?
I could ask.
Okay. Dr. Igo.
What is possible to say about effect substrate on film? You use silicon, yes? Or what is your idea to?
Yes, yes. The substrate is a very important parameter.
Yeah.
In this case, of course, I agree with you, especially in the Bismuth Ferrite thin films. But in general, if we need to use for the substrate, the BFO for technological applications, we think about conductivity substrates, of course. If you want to explore the photovoltaic properties of bismuth, you need to use, for example, a transparent substrate, but conductive. In this case, the silicon substrate, I think the main property can be associated with the epitaxy in these films. But the epitaxy can be also obtained by other ways. I don't know if you are interested in the epitaxy or in the final properties of the film. Regarding electrical properties, in this case, if you deposit the BFO on the silicon to explore these electrical properties, it is usual to use another kind of electrode deposited on the surface, right? Not like a capacitor, okay? But the main question, Igor, in my opinion, is that we have in the literature different reports, different results on the VFO thin films. In my opinion, my conclusion is that prepare VFO film is too hard. It's not easy. We need to a hard control to prepare a good sample to obtain specific properties. Okay.
Yeah. Thank you very much
Thank
for the
you.
response. And we have time for one more question. If there is a quick, small question, if there is one more question. No.
Yes.
No. Yes, there is a question from Leon. Yes.
Yes.
Go ahead.
May I have a question?
Yes.
Maybe I have skipped this, but what about the intrinsic defect, like not vacancies, but other types, like the same atoms which are shifted to another position or somewhere where it shouldn't be? May such defects can be in your materials in perovskites?
Okay. Thank you. Yes, I understand you. As observed in my talk, sometimes you can introduce a specific atom in the structure, like lanthanum, zirconium, and niobium. But in my opinion, in this case, you are changing the nature of BFO structure. In my opinion, you don't have more the same structure. Okay. The question is not only oxygen vacancies are responsible for the physical properties, as often discussed in the literature.
Yes.
There are another possibilities like bismuth vacancies and iron vacancies. This result, in particular, suggests that the complex defects must be investigated. I agree with you. Yeah.
Okay, thank you.
Thank you very much.
Thank you. Thank you for the question, as well as let me thank Professor Araujo for the very interesting talk. It's so informative. Professor Araujo, we would like to have your cooperation for the coming years as well. Thank you. Thank you very much for
Thank you very
nice
much.
presentation. Okay.
Okay. Good afternoon, everyone.